Microchip technology provides an extensive product portfolio of 8, 16, and 32-bit microcontrollers and digital signal controllers to help our customers select the device which best suits the needs of their application. As time progresses, customers may be faced with the need to expand or even downsize their application, to add, optimize, or otherwise modify the design. In this video, some key considerations are discussed when migrating between Microchip's 8-bit and 16-bit microcontroller and digital signal controller product portfolio. Let us consider optimizing a system's response to events and execution of tasks.
A design may need to further optimize how quickly it responds to external or internal events, or perhaps execute more elaborate math operations so that the device can perform a given task and then re-enter a lower power mode. Both 8 and 16-bit architectures feature a wide selection of core-independent peripherals designed to minimize task execution time. However, there are times when a task must be handled in software. In this case, a customer may wish to consider migrating from an 8-bit microcontroller to a 16-bit microcontroller or even a digital signal controller. The 16-bit architecture features a software stack alternative which simplifies complex software operation using multiple nested subroutines along with faster system clock options. The DSPIC line of digital signal controllers feature the capabilities of a microcontroller, including peripherals and lower power modes, while adding hardware that enables the performance of a digital signal processor. In addition to executing embedded firmware faster, more memory may be needed in some applications to accommodate more elaborate software applications. 8-bit microcontrollers provide up to 256 KB of flash program memory and up to 16 KB of data SRAM storage. 16-bit devices can accommodate up to 1 MB of program flash and up to 96 KB of SRAM data memory. Low power is a key concern in many embedded applications, and both architectures feature various capabilities to minimize power consumption. In conjunction with industry-leading low current consumption, doze, idle, and sleep modes of operation provide flexible CPU and peripheral clocking options with the ability of many peripherals to operate in these lower power states. Additionally, the 16-bit devices further provide a deep sleep option which further reduces current consumption by removing power to RAM memory cells. 8-bit microcontrollers are typically designed to be as small as possible while heavily integrating capabilities with package pin counts ranging from as few as 6 pins to packages with 64 pins. However, there are instances where the application requirements demand additional pins. In this instance, customers may wish to explore 16-bit devices which offer packages starting at 14 pins up to 144 pins. Both 8 and 16-bit architectures make it easier to migrate across platforms by providing flexible pin configuration of digital signals through the peripheral pin select functionality. In this way, most digital peripheral signals can be routed to a variety of user-selectable pins to simplify board layout complexity and signal routing to help minimize application redesign. Pins can even be assigned on the fly with mechanisms in place to temporarily or permanently lock pin configuration at runtime to avoid pin signal uncertainty. 16-bit devices also feature the flexibility to choose from a few program debug pin connection options while also adding the ability to simplify production programming diagnostics by providing a JTAG boundary scan option. Additional pin capabilities on many 8 and 16-bit architectures include the ability to apply pin signal slew rate control, interrupt on change, an open drain control option, and the ability to apply on-chip weak pull-ups with 16-bit products also featuring weak pull-down options on select devices. In applications where high current sourcing or syncing is required on I/O pins, both architectures boast 25 mA source sync capabilities. Applications requiring higher current on the I/O may benefit by using recent 8-bit devices that feature 50 mA source sync currents on most pins, with some select 8-bit devices featuring 100 mA source sync capable pins. Recent 8 and 16-bit microcontrollers and digital signal controllers focus on peripheral integration, especially those peripherals that can operate independent of the core, minimizing the amount of software needed for the application. Both architectures feature similar peripherals, but there are some key exceptions. Both 8 and 16-bit families feature a great deal of analog integration, including analog to digital converters, operational amplifiers, stable voltage references, and more. Newer analog-to-digital converters feature more core-independent operation by integrating tasks like voltage level thresholding to trigger interrupts when a voltage range is exceeded or met. Many newer devices further feature the ability to automate tasks like accumulation, averaging, thresholding, and low-pass filtering with A to D resolutions up to 12 bits. 16-bit products add to these features with up to 16 bits of resolution, decimal result representation, and faster conversion rates of up to 10,000 kilosamples per second. Faster comparator operation requirements can make use of 8-bit devices, which can trigger an output in as little as 50 nanoseconds, with 16-bit devices able to trigger in as little as 15 nanoseconds. Integrated digital to analog converters can be used to provide a finer resolution when used with on-chip voltage references to other peripherals, with 8-bit devices providing up to 12 bits of resolution and 16-bit devices providing up to 16 bits of resolution on select products. Designers requiring PWM waveform generation in their application have many options to choose from. 8-bit microcontrollers provide options for up to 16 bits resolution, with additional peripheral capabilities that accommodate for various bridge drive topologies, PWM waveform steering, and safety features like integrated deadband delay. 16-bit devices expand on these capabilities with select products offering fine-edge placement 16-bit PWMs with 250 picosample time resolution and options for PWMs optimized for motor control or switch mode power supply applications. Flexible timer options on 8-bit devices can interface with both on and off-chip signal chains with resolutions up to 24 bits. 16-bit devices extend timer resolutions up to 32 bits. Both architectures also include peripherals designed to ease the development of safety-critical applications, such as those requiring UL or Class B certification. Monitoring of software integrity is made easier using cyclic redundancy checkers to monitor for inadvertent changes to application firmware, while windowed watchdog timers eliminate software hang-up conditions. Select 16-bit devices further implement a deadman timer, flash error correction code, and RAM memory built-in self-test for further monitoring application firmware robustness. In addition, some of the 16-bit devices are also supported with functional safety manuals and diagnostic software to ease ISO 26262 compliance for ASIL applications. Standard communication peripherals are integrated on many 8 and 16-bit devices, including I2C, SPI, USART, CAN LIN, full-speed USB device, and more. Designers requiring integrated inter-IC sound, CAN FD, DCI, or full-speed USB on the go will want to take a look at Microchip's 16-bit products. Finally, human interface applications can be made easier using integrated capabilities on both architectures, including segmented LCD controllers and capabilities to facilitate capacitive touch sensor development. Select 16-bit devices further feature a graphics controller module specifically designed to directly interface with display glasses and individually control pixels in the screen.
These capabilities on Microchip Technology's 8-bit and 16-bit microcontrollers and digital signal controllers, along with a focus on easy-to-use software and hardware development tools, provide a flexible and streamlined solution to help optimize the design process. For more information, please visit microchip.com/migration.